in-person attendees, because this talk is Zoom talk, and in general, when we have Zoom talks, please come here to this microphone to ask questions, because that other microphone, I think even people in the room don't hear anything, and people on the Zoom definitely do not hear it. Sorry for interrupting, Pradeep. You can go on now.
Yeah, absolutely. So yeah, great to be here. So what I'm going to talk about today is, in addition to the wonderful work that you have been seeing in the workshop, what I wanted to focus on was on objective evaluation criteria. So most of the work that we see, and the very nice work that we see in explainable AI or XAI, the one caveat though is that a lot of it is typically evaluated in a qualitative fashion. So in the sense that what's typically considered to be the best way to evaluate it, well, show human evaluators a bunch of explanations and gauge how satisfied they are. You could also measure things such as how much faster they are able to achieve whatever task that they are planning to achieve. Now, these kinds of qualitative evaluations might seem inevitable to some extent, because ultimately, if you think about explanations, we want to map this 100 million parameter, 1 billion these days, it keeps increasing, parameter model to essentially the human mental space. And so the problem though is that if you think about this as a mapping, to think about what humans can understand is highly ill-specified. And in some sense, we don't know how to characterize that. And so obviously, given all of these ill-specified nature of essentially the range of this mapping, qualitative evaluations might seem to be the only thing we could do. So one of the questions we wanted to ask was, can we come up with objective criteria in addition to these qualitative evaluations, which again, given essentially this, what I just discussed, will always be there with us. So can we augment that with some objective criteria? So this might seem tricky, right? Again, because if you think about explanations as mapping the models to humans, humans' mental maps. So how do we do that? Well, the way we look at it is that ultimately, if you think about an explanation as, again, a mapping from a model, in some sense, we should be able to connect the explanation to the model, right? And obviously, if we look at different classes of explanations, this notion of connecting the explanation to the model would differ. And so that's basically what we do. We actually do not come with a single criterion to rule them all, so to speak, but depending on the categories of explanations, we would have different ways to evaluate them. So we look at two broad categories, based explanations and sample-based explanations. So let's look at that separately. So feature-based explanations, these are the most prominent types of explanations that you would have seen, right? So again, if you have a test image, then you would have various feature explanations that, for instance, would either highlight parts of the image that the model is focusing on, or with saliency maps, they could even give you color maps for the weights in addition to what are the regions of the image that the model is focusing on. So far, so good. But the problem is that the moment we are going to qualitatively evaluate explanations, many have found that, unfortunately, you can have explanations that need not look at the model at all, that would only look at the test image and would give qualitatively reasonable things about the test image, such as, for instance, edges. And that is, so if you show these, so if, for instance, I just show the edges in an image to a user and ask them, hey, are these sets of edges in the image as an explanation of a complex model reasonable? Most people will say, yes, that seems like a wonderful thing. The model is doing something wonderful. The problem is this explanation did not even look at the model. It just was an edge detector, right? And so what they found is that many classes of explanations fail what they call the sanity check, where just changing the model is not changing the explanation. Thanks for fixing the noise. Yeah, it's much better now. So to address this point is what we essentially wanted to focus on. So you think of this kind of a mismatch between the explanation and the model as what we call infidelity. And so the way we wanted to formalize that was by asking the question, does the explanation have the information, if not all information, some key information about the model? Now, obviously, right, especially when we are dealing with such complex models, we cannot really expect the explanation to have all of the information about the model, right? Because then the only way to get that is to have the entire model itself, unless the model is compressible in some way. But by and large, this is tricky, or most likely impossible. But typically, at least locally, here, the locality is with respect to the test point, test image. Can the explanation, at least in the locality of the test image, explain the model? And the reason there is some hope here is that even though the model itself is globally complex, locally it could be simple. And in general, of course, locality is in turn ill-specified, but you can always have a sufficiently localized region where the model would seem simple, right? And so that's really the goal behind many of the explanations. And so we leaned into that and tried to come up with an objective measure to evaluate the local fidelity of an explanation to a model. So the way the explanations typically work is that you have a test input, and then you have typically some perturbations delta. So in other words, you take your input X, and then you perturb it to X minus delta. So what happens to the model output? It goes from, so here, imagine F is the model. So the model output goes from F of X to F of X minus delta. So the model output gets perturbed as well. So the question then is, can I get a sense of this model perturbation just from the explanation? So in other words, if I remove a certain portion of the image, can I figure out how the model's prediction might change just by looking at the explanation? And I can, of course, have many kinds of perturbations. The simplest thing really would be to just change a portion of the image. Okay, maybe just blank out a portion of the image. So just think of it as that, as a running example of a perturbation. So let's now think about in explanation E as taking in a model and a test input. And if you want to think in terms of saliency map or feature importance maps, you get one value for each of the P features. Okay, so again, in the context of image, these would be the pixels. So I get one value per pixel. So given this setup, we define an infidelity measure as saying, can this explanation give me information about the perturbation, the model, the effect of the perturbation on the model output, which is captured here, whether it can actually describe this model perturbation. And one way in which you characterize that is through essentially a simple linear model. Okay, so I take the explanation, and if I fit a linear model given the explanation, can it actually describe the model, the effect of perturbations on the model? And obviously, when the models themselves are, the perturbations themselves are random, so we can think of this delta perturbation as a random variable. So then I would need to look at the expected fidelity. And so that's our expected infidelity. So that's what we call this infidelity measure. So broadly, in a nutshell, we are asking, can the models explain the influence of perturbation? So there's a question, explainable depends on the context. Explanation should include some reference to confidence of the inference outcome, and so on. maybe I'll come to this. Maybe I'll come to the question, since that seems like a broader question.
So the practice until now was that people write in the chat questions, and then Deepti will moderate and ask you in the end. So you can just go with your presentation until the last 5 minutes, and then we can go back to these things.
That sounds great. Yeah, absolutely.
Thank you.
So given this complicated looking expression, one of the things we can do is say, hey, what are the optimal explanations? So I'm sure that's essentially just the saliency map, which is the gradient of the model at the test input, but integrated from some reference to the test image. And what the optimal explanation is doing is really some sense on essentially this perturbation. So that's interesting. So which is that the least infidelity explanations are really some smoothing of integrated gradient. And obviously the smoothing depends on the nature of perturbations. And one of the things we found is that across a series of feature-based explanations, they are optimal with respect to infidelity, except with different perturbations. So one of the things we did was just have a slightly different notion of perturbation than what is considered in the literature. So we looked at removing just square patches from an image instead of just removing individual pixels or infinitesimal perturbations and so on. And so then if I define perturbations that way, I can then define the optimal explanation. And so that's basically this column on the right. So what we see is that we get more contiguous, compact saliency maps compared to the other saliency maps. And again, this essentially allows you to define your own perturbations and derive new explanations. Existing explanations. Now, we can move from just feature importance weights or saliency maps, which in general are very difficult to interpret other than in a kind of general sense, right? Because it's very difficult to scrutinize the individual feature importance weights. So it's much more common to give just a feature set where we just give the set of relevant features. So in cases like that, how do we then talk about fidelity of the explanation of the model? So in cases like this, where you're given such highly partial information, just the set of relevant features, quantitative connections of this explanation of the model might seem difficult. But the thing is, we can actually use robustness analysis to, again, make the connection quantitative. So the way we do that is basically, let's think about what important features means. So if I fix the values of important features and just change irrelevant features, so I have a cow on a field, I just change the background, right? It goes from grass to, I don't know, green grass to just brown grass, then it should not change essentially the object, the foreground, right? So if I change the irrelevant features, it should only weakly affect the model prediction. Similarly, if I say that, hey, these are the important features, then even if I change the important features ever so slightly, that should strongly affect the model prediction. So you have these two different effects on important versus unimportant features, and we can quantify this, even if you just tell me, hey, these are my important features. And so in particular, what I can look at is the minimum perturbation I would need to change the model prediction, where the perturbations are restricted to only perturbing pixels in the set S. Okay, so obviously, if the set S are unimportant features, then I would need a large perturbation, or maybe no perturbation could possibly have an effect. But basically, to have an effect, the perturbation needs to be very, very large. But when the set S is important features, then even a small perturbation can have a large effect. So this is a way for me to quantify then whether the set of features you are giving me are important or not. And one of the things we can again do, just as we did with infidelity, is that we can optimize this robustness measure to give you the optimal set of important features. And so this is just MNIST images. And what we found is that the features that we came up with were, so here, many of these like saliency maps are feature importance weights, right? But you can essentially look at the top 20% magnitude of the importance weights to get a feature set. And so what we then are plotting are just these important feature sets. And what we found is that many of these guys give you the pertinent positives, but they don't give you the pertinent negatives, in the sense that there are certain features that should be absent. Like here, for instance, if I have these pixels that are present, it will go from a 7 to a 9. And so we want to highlight them as pertinent or important. And some of the ones actually miss that, like SHAP, for instance, clearly is missing some important features, whereas we are actually explicitly pointing those out as important. Mainly because we are explicitly optimizing for robustness. And similarly, when you actually look at the saliency maps, you get much more compact saliency maps, mainly because it really cares not to give you irrelevant pixels, right? So when you see a lot of these noisy pixels, the robustness analysis would explicitly discourage the explanation from giving you irrelevant features, because if the robustness analysis would be allowed to perturb those irrelevant features, right? So that's basically one of the advantages of this. So you can both get an objective evaluation, and whenever we get an objective evaluation, you can optimize it to get better explanations. And then finally, let me just talk very briefly about, so I guess I have 5 more minutes. So let me just talk briefly about sample-based explanations. So if these are much less common, mainly because of computational reasons, but they are, if you think in terms of human understanding, these are the easiest for people to understand. So for instance, if I have this particular image as my test image, and I essentially can ask, what were the training samples that were most important for the model that you are deploying, that were most influential in the model having arisen at whatever the prediction it has come to. And so we do that with humans as well, right? So if there is somebody you look up to, you can ask them about the books, ways, maybe people who had influenced them, right? So that's usually very instructive. And so here with this grizzly bear, we can essentially look at and say that, hey, these seem to be the positive training examples, in the sense that these training examples, when present, would having been present, were very influential in a positive way. And these training examples, having been present in the training set, were influential in a negative way, in the sense that they were trying to push the model away from grizzly bear. Now, the most popular sample-based explanations are influence functions, which make a lot of sense, in the sense that they are very similar to saliency maps in some sense. What they look at is basically, if I infinitesimally increase the weight of a training point, then would it affect the model that would be trained? And so give me training examples that would be most influential in that way. But looking at this more broadly, we can essentially ask about the positive and negative or representers as basically, let's actually jump to an example, and that'll become clearer. But before I jump into the specific example, let me just define one notion of what we may want from sample-based explanations. So again, F is my model, X is my test input, and XI is the training input. And so this should give me E, sample-based explanation should give me the importance of the training example XI for the model's prediction F at the test input X. Now, one of the things I may want, just to normalize the predictions, or to distribute the prediction or the loss of the prediction among all of the training examples, is to say that the sum of the importance weights should sum up to something meaningful, like the model prediction. It could also be the loss of the model in some way. Now, this by itself is less meaningful, but what if this explanation can be cast in this format, where there is a notion of similarity between the test input X and the training input Xi, and some global importance of the ith sample. It would be great if this can happen, right? Now, the interesting thing is that if the model that you train is trained, is learned from within an RKHS with respect to your some kernel K, then we have all seen represented theorems that then say that your f of x should have this form, right? Where these Xi's are the training data points, training inputs. The problem, though, is that the typical models that we train are not trained in this way, right? We don't just do RKHS regression. We just train deep nets instead. What we then showed is that even for deep nets, you can actually cast this in this format for particular kernels. And so what you can then get is the corresponding kernel and the global importance weights, and this would then be your explanation. It's very natural and very meaningful. So you get a global importance weight per sample, and then you also get the similarity. So this turns out to be very, very nice in the sense that if you, here is an example, a rhino is predicted as a rhino. I can look at the positive training examples, and those are images of rhino. So it was important that these have been present in the training data. And then if you look at the negative training examples, they look similar to rhino, but they are actually other animals. So these are the most confusing samples from other classes. Okay, so this is basically, so in large-scale multi-label classification, we know that such negative sampling is pretty critical to training a good model. Here, essentially, this tells us that, you know, part of the reason why these deep networks are so great is that they are explicitly using these negative representers. So if you look at things like influence functions, they aren't that good with respect to these positive and negative influences. So one of the things we found fascinating was that this was very useful to debug models. So this, as you may have seen in some of the talks, is a great use of explanations, because you can use those to debug your models. So here is a model that overall accuracy was pretty high, but it was making a mistake on this image. True label is an antelope predicted as a deer. Why is it making the mistake? Let's look at the negative representers, the most confusing samples, right? So if you look at these, what you see is that you do see a small antelope in the images, but then what's happening is that these are small and they are together with the bigger animal. And so the model is essentially suppressing, if it sees small antelope, it's suppressing the label antelope. Okay, so once you look at this, it's pretty obvious what's happening. So the solution may also seem obvious, right? Clean up the data or just do multi-label and so forth. But at least we get a sense of why the model is doing what it's doing. So that's basically what I wanted to talk about, just as a whirlwind tour of 3 qualitative or quantitative ways to evaluate explanations. And so that's really something that we think there should be more of, in the sense that whenever we propose an explanation, typically underlying it is some objective evaluation criterion. It would be good to bring those out so that we can always have a suite of objective criteria that we can run any proposed explanation under. Okay, with that, let me just stop. Thanks.
Okay.
Okay, so maybe I can go over the chat question. So is there a consensus understanding that explainability or explainable is the notion that the output should be understandable?
So can you actually, because the people who are attending in person will not see the question, can you just read it once again clearly, and then you can answer? Thank you.
Yeah, absolutely. So the question was, is there a consensus that explainability is synonymous with the output being understandable? So it's perhaps by output, perhaps you mean the model itself, or rather why the model made the output, had the output that it did, and whether this should be understandable. Largely, yes. So the way I look at it, mainly look at it, is that the model itself is this gigantic thing with so many parameters, inscrutable, but can we take that and map it to a form that humans can understand, at least in the locality of the test input? So that's basically, so we do want it to be understandable for a particular test input. So there's another question on what kind of matrix are you using for robustness criteria? So we are not using a matrix, but we are defining the robustness criteria in this very specific way, where we essentially look for the minimum perturbation such that the model prediction changes. So the norm P perhaps is relevant here. So here you can look at various norms of the perturbations, L infinity, L2, all of these yield similar answers. Yeah, so there is no other matrix that we use in this context. And then there was another bigger question. Actually, let's go with this. What kind of DNNs have small norm in a RKHS? Is there an accuracy trade-off with this assumption? For instance, what do we see with neural networks and NTK versus ResNets? The thing though is that unlike NTKs and various fixed kernels, whether they be hierarchical or not, and with the DNN, one way to think about a DNN or any of these neural models is that they learn a kernel and then they have a linear model sitting on top. Now, all the complexity goes into really learning the kernel or learning the feature map. The two are really the same thing. So ultimately, with respect to its kernel, it'll have a small RKHS norm. And so this is essentially the crux of the matter. So with respect to a fixed kernel, a DNN having a small norm is an extremely strong assumption. But with respect to its kernel, it'll have a small RKHS norm. This is almost by definition. And so that's basically what we showed, that for a DNN, it has a kernel under which it has a small RKHS norm. So that's the critical.
We have one or actually two more questions that will be from the audience, and then we're going to move on to the next speaker.
Sure. Yeah.
My question is, why is perturbations a good way to quantify explainability, as opposed to if I take an explanation, then it should be good or sufficient for the prediction, and just measuring performance based on the explanation as opposed to on the whole input should also be a way to quantify?
That's a very good question. I think because perturbation seems like, why are we even bringing perturbations up? That's a very good question. So the way to think about this is that ultimately, if you think about the model at a particular test input X, right? What does it mean for the explanation to give information about f of X? Right? So how do you even formalize that? So the only way to talk about whether we have information about the model, model's predictions is really in a small locality around X. So it's there that we have uncertainty, right? So let's say I show the model's prediction at for a particular image, and I say, hey, here is the explanation. How do we then test whether the human has actually understood how the model behaves. The only way to check that is on a different test input, right? And so obviously, to show a completely different test input and expect the explanation to have given the information is too much to ask. It would be great, in which case these deltas would look very different, in which case these delta would be more global, but that's really what we are trying to capture. We are just trying to formalize exactly what you said, which is the explanation should give some idea of how the model behaves. The perturbation just comes up in defining the locality around the test input in which we are going to do that.
Okay, last question.
Hi, so I think for this infidelity, you mentioned that depending on which perturbation you consider, certain explanation becomes optimal. But then again, the remaining question would be, okay, which perturbation should we consider? Because depending on, then we cannot really, compare the explanation because it becomes optimal for different perturbations.
That's right.
So how can we compare those explanations, or how can we choose which perturbation to consider?
That's right. So that's a good question. I don't have a clean answer for that. So this is probably where domain knowledge is relevant, where if you have a certain sense of perturbations or locality that makes sense, then that is what should be used. But if you have no idea about the perturbations that should be used, then certain standard ones like noisy baseline, where you have some reference image and you talk about perturbing a subset of the input to the corresponding reference or default input. So basically, this is a very reasonable one. But to go beyond this, that really depends on, I think, the domain knowledge. So it also is related essentially to the locality, where what is the locality around the test input where you want this explanation to have fidelity. It would be great to have this be over the entire space, right? But that's impossible. And so, So in general, what I would recommend is really when you want to evaluate a candidate explanation, then just use like these baselines, noisy baselines, subset baselines, because these really capture what we typically have in mind. But if you have something much more specific in mind, then one should use that.
Okay, thanks a lot. Let's thank the speaker once again. This was a great talk. Thank you, Pradeep, once again, and we'll see you soon at the panel.
Thank you so much, Pradeep. See you soon.
Okay, Deepti, you can introduce the speaker. I'm just setting up the presentation slide.
Sounds good. It's a great pleasure to introduce our next speaker, Dr. Serena Young. She is an assistant professor of biomedical data science and computer science and electrical engineering at Stanford University. Her research interests are in the areas of computer vision, machine learning, and deep learning, focusing primarily on applications of healthcare. I think she's done an amazing range of work on building models that are more transparent and interpretable within the domain of medical data and other domains as well. So very excited to hear your talk, Serena. The stage is yours.
Thank you very much for the introduction. And let me just get this started. Okay. Okay, so today I'd like to talk about some of our group's ongoing work on multimodal